In the late 17th century, the world was teeming with intellectual curiosity and scientific exploration, marking the vibrant period known as the Age of Enlightenment. During this era, one of the universally accepted beliefs was the purity and simplicity of white light. Scholars and laypeople alike held the conviction that white light was indivisible and pure, a fundamental essence untouched by complexity. This belief was not just a scientific assumption, it was almost a philosophical and spiritual axiom that light, especially sunlight, was the ultimate symbol of clarity and purity. The idea that light could be anything other than a simple singular entity was almost heretical in scientific circles and beyond. It was within this backdrop of entrenched convictions that Isaac Newton began his groundbreaking work, poised to challenge the very foundations of what people thought they knew about light. In his humble Cambridge study, surrounded by the tools of science and the heavy air of anticipation, Newton was about to embark on experiments that would not only question the prevailing views of his time, but also fundamentally alter our understanding of the natural world. His curiosity and rigorous scientific methodology set the stage for a series of experiments that would turn the scientific community on its head. Isaac Newton, a figure already renowned for his work in mathematics and physics, directed his inquisitive mind towards understanding light. He began with a simple yet profoundly effective experiment involving a beam of sunlight entering a dark room through a small hole. This setup was crucial as it isolated the sunlight from other variables, allowing for clear observation and manipulation. Newton then positioned a triangular glass prism in the path of the sunlight. As the light passed through the prism, something unexpected occurred. The light did not remain white. Instead, it fanned out into a beautiful spectrum of colors, displaying a continuous range from red to violet. This was the first recorded observation of what we now call the visible spectrum. The moment the spectrum appeared on the wall of his darkened room, Newton must have realized he was witnessing a revolutionary discovery. The simple white light he had introduced into the prism had unveiled its complex nature, contradicting centuries of established thought. This experiment was not just a demonstration of scientific technique, but a bold challenge to the dogma of the time. Upon observing the spectrum, Newton identified 7 distinct colors: red, orange, yellow, green, blue, indigo, and violet. This categorization was more than just a scientific observation. It was a new way to understand the very nature of light. Newton proposed that white light was not pure, but a composite of various colors that could be separated and then recomposed. Newton's insight into the spectrum was meticulous. He noted how each color bent at slightly different angles when passing through the prism, a phenomenon he later termed as dispersion. This bending occurred because different colors travel at different speeds when they pass through various mediums, such as the glass of the prism. This discovery not only demonstrated that white light was made up of different colors, but also hinted at the varying properties of light that could be further explored. Newton's work laid the groundwork for a more detailed study of light's characteristics, such as its speed, its interaction with materials, and its wave-like behaviors, which would be pivotal in the development of optical science. Newton's explanation of light dispersion was revolutionary. He theorized that light is composed of particles that could be refracted by passing through a medium, such as glass. This refraction caused the light to display its constituent colors, much like a painting being slowly unveiled. Newton's particle theory of light was initially controversial, as it contradicted the prevalent wave theories of light proposed by others. To further validate his theory, Newton conducted numerous experiments, meticulously documenting the angles of refraction for different colors. His mathematical approach to optics was a significant shift from the largely qualitative descriptions that had preceded him. This rigorous quantitative analysis helped establish a more empirical and measurable understanding of light. Moreover, Newton's work on light dispersion not only enhanced our understanding of optics, but also contributed to the broader field of physical science by introducing a systematic approach to scientific experimentation. His emphasis on empirical evidence and mathematical precision would come to define the modern scientific method. The immediate impact of Newton's findings was profound. The scientific community was forced to reconsider and eventually abandon the long-held belief in the purity of white light. This paradigm shift was not just about optics. It symbolized a broader movement towards questioning and scientifically testing the assumptions of natural philosophy. In the centuries that followed, Newton's theories laid the foundational principles for the field of optics. His work influenced generations of scientists, including those who would later refine the wave theory of light and integrate it with the particle theory, leading to the development of quantum mechanics. This integration is a cornerstone of modern physics, affecting how we understand everything from the behavior of tiny subatomic particles to the vast movements of galaxies. Today, Newton's work continues to influence scientific thought and research in myriad ways. His discoveries are taught as fundamental principles in physics classes around the world, from high schools to prestigious universities. The methodologies he pioneered are still in use, underpinning the scientific processes that drive innovation in technology and industry. Isaac Newton's insights into the nature of light have echoed through the halls of science to the present day. Modern optics, a field that encompasses everything from the design of microscopes and telescopes to sophisticated photographic equipment and high-speed communication technologies, owes much to Newton's pioneering work. For instance, the understanding of light dispersion has direct applications in the creation of optical lenses that correct for color distortions known as chromatic aberration in cameras and eyeglasses. Furthermore, the principles of light refraction and dispersion are used in the development of various optical devices, including prisms and spectrometers, which are essential tools in scientific research and industrial applications. Moreover, Newton's work has been instrumental in the development of technologies such as fiber optics, which rely on the principles of light reflection and refraction to transmit information across vast distances. This technology is the backbone of modern telecommunications, including internet and cable television, fundamentally shaping how information is shared and consumed globally. Beyond the realms of science and technology, Isaac Newton's discoveries have also permeated popular culture and education, shaping how light and color are understood in various artistic and academic contexts. His color theory influenced artists and theorists, contributing to the development of color palettes and the understanding of color relationships in visual arts. Educationally, Newton's optics experiments are a staple in physics curricula worldwide, often serving as a student's first introduction to the empirical scientific method. His work fosters a critical understanding of how to observe, hypothesize, and experiment, fundamental skills for any scientific inquiry. Moreover, Newton's approach to science as a blend of empirical evidence and mathematical rigor continues to inspire cultural narratives about the nature of discovery and the role of scientists. His life and work are often cited in discussions about creativity in science, the importance of challenging established norms, and the unending quest for knowledge. Isaac Newton's exploration into the nature of light was more than just a series of experiments. It was a profound shift in the understanding of the natural world that continues to influence both science and culture. His ability to question established beliefs and rigorously test his hypotheses set a new standard in scientific methodology, one that remains at the core of scientific inquiry today. The legacy of Newton's discoveries in optics extends beyond the technical and into the philosophical, encouraging a mindset of curiosity and critical analysis. It reminds us of the power of a simple question to unlock complex truths and the potential for these truths to transform our understanding of the universe. As we continue to explore and understand the mysteries of light, from quantum mechanics to optical technologies, Newton's work serves as both a foundation and a beacon guiding ongoing inquiries and innovations. His insights prove that even the most fundamental aspects of our universe can hold surprises waiting to be uncovered by those who dare to look closely and think deeply.